I guess I'll just have to speak loud. Our speaker today is Michael Ross. He received his AB from Dartmouth in '71, his PhD in chemistry at Caltech, and completed a postdoc in molecular biology at Harvard. Mike has served as a Thayer School board member since 1992. Dr. Ross is currently a venture capitalist at SV Life Sciences, but in a previous life he was the 10th employee at Genentech, where he worked for 13 years. Following that, Mr. Ross worked at several very successful biotech companies, and he's here today to speak to us about healthcare venture capital in a state of flux. As a separate announcement, I would ask as a courtesy to our speaker that you refrain from using laptop, please.
Thank you very much. I'm going to divide this talk into two parts. I think you'll be able to tell the difference between the two. The first part is about venture capital, and the second part is about 5 companies that we at SV, well actually I personally have invested in that have what I would call really cool technology associated with them. 2 of which started here, I might add, but they all are a little bit different from each other, and I'm not going to go into great depth with any of them because I don't have time to talk about 5 companies in venture capital at the same time, obviously. But just to give you a taste of the kind of science and the kind of, if you will, molecular engineering that goes on in companies that are funded by venture capital. And with that, I'm going to start off first by, without a slide, explaining a little bit of the food chain of venture capital. So I'm hired, and as an example, Terry is hired, by our firms to invest money which comes from various kinds of sources. I'll give you a few examples. Endowments are one. Pension fund, public pension funds of states. Teachers' pension funds in states that are so big they've got 2 kinds of pension funds, like California or Wisconsin. Private pension funds of large corporations like AT&T, General Motors, well, maybe not anymore, but Northrop Grumman in our case, the World Bank. So large organizations that have pools of capital that they want to have long-term higher than normal returns on, invest in venture capital. These people who manage that money have almost, well, very rarely do they have any technical training. They are folks that turn over reasonably rapidly. In other words, from one fund to the next, we raise funds every 4 years or so. You're lucky to see the same person. Some of these organizations, they stay, but often they turn over. Our entrepreneurs turn over, and just to give you a view, we're not supposed to turn over, okay? So we're in the lobster trap business. We go into the lobster trap when we join venture capital, and it's considered very bad form until you keel over to leave. Because steadiness, it takes a long time to figure out whether you're any good at this business, and steadiness of the partnership of the people who are doing the investing is highly valued by the people who put the money in. Oh, that's the same guy. Okay, fine. So when the team changes, they don't like that. So it turns out I like what I do, so I don't mind being in the lobster trap, but it was something I didn't actually understand when Terry didn't tell me this when I joined a venture firm. So I didn't understand that, but I do now. So I've been doing this about 10 years, and 20 years, not quite 20 years before that, doing other things in the healthcare business. So I don't have any specific slides on SV Life Sciences. And by the way, there may be a few advertisements that show up on the slides because I stole these from fundraising activities. I tried to get rid of them, but I may not have done a terrific job. So there may be a few things. I'm going to try to make this as generic as possible. and talk about why there is a venture capital industry in healthcare and the sorts of things we do. I'm going to give you 1 minute now of, oh, by the way, how the total, well, you want questions at the end? Yes. So, okay, 50 minutes then. Good. I think I can handle that. So, why is there healthcare venture capital? I'm going to go through that. What's the state of the industry? What does Obamacare have in store for us that's new and wonderful in the investing business? And what are the challenges that we as an industry are facing? We globally means healthcare providers and inventors, and we more narrowly those of us that invest in it. So first 1 minute about my company. So SV Life Sciences is a spin-off of Schroeder Ventures. So SV stands for Schroeder Ventures. The name got disappeared by the bank Schroeder Ventures when they wanted it back, and for economic reasons that was a good thing for us too. So now we're just SV, but it started off as a spin-off of Schroeder Ventures. Schroeder Ventures started off as a single, very large European-based private equity firm, and a couple of individuals were in it decided that around 1991 that they should spin off from Schroeder Ventures and start a healthcare-only fund, and in the United States. So we are now, and they started raising funds. The first fund was about $100 million, and since then we've raised 5 funds. We just finished raising a $520 million fund this year. That was just a load of fun. In case you hadn't noticed, this was a really crummy time to be raising a fund, and we did fine, but it took us much longer than we wanted to. And I guess I just feel very blessed that we were actually able to do that. And that should give us capital for 4 years to invest. We invest in biotechnology, which broadly means drugs, biopharmaceuticals, and diagnostics, half of our fund. A quarter of our fund, medical devices, which is anything from diagnostic devices to knee implants, something near and dear to the heart of this college, spinal implants and so on, and a quarter healthcare services, which could be everything from healthcare IT to contract research organizations that provide services to biotech companies and pharma companies, to home health care in a nursing home kind of setting. So just about anything there. So diversified, but all healthcare. We have 3 offices, London, Boston, which is our head office, and San Francisco, which is where I work. So today, again, this is sort of the agenda for what we're going to talk about. I'm going to talk a little bit about the healthcare market, which broadly will tell you some of the economic parameters that we live within. A little bit about the life sciences VC marketplace and how it's changing, hence the title. Some key dynamics those are positive, by the way, when we get there. Key dynamics in biotechnology, things that will actually drive us. And then 5 companies which are quite different from each other, actually, and the fun part of what I do is interacting with great entrepreneurs and great scientists. So why is this an interesting business to be in? Healthcare is still, for most diseases actually, a partially or an unsolved problem. We have ways of mitigating issues, but very rarely do we have ways of solving issues. And the last company I'm going to talk about really plays to one of those, and that is very shortly in the United States, 30% of the people in this country will have diabetes. It's just amazing, at least it is to me. And the treatments for and this is mostly type 2 diabetes, the treatments for type 2 diabetes these days are just not very helpful, except losing weight, which nobody seems to be able to do. So, which is why 30% of the people have it, for the most part. I'm not going to read, by the way, I'm not a big fan of reading all the slides, so if you would be so kind, when I'm talking about what's on them, is to look at the data here, because there's a lot of data, and if I read all the slides with all the data, A, you will be bored, and B, I will be bored. So, but there's some interesting data here about what's happening, how many people are getting sicker, and in spite of the fact that we've got better treatments, both from devices and from drugs, and I'll go into the positive side of that in a bit. But it is a large, large market and a very important one for society. Healthcare spending, and I guess I just look at the lower right-hand corner of this, has grown in fits and starts, actually. It's interesting how it levels off and then it rises and then it levels off again. But it is a big percentage of GDP in the United States, much less so in other developed countries. And of course, if you've been paying attention, that's the government and the politicians and the rest of us have been debating, whether it's worth the larger amount that we pay in this country. It's very unlikely to go down. That's just the way it is. One is talking about trillions of dollars, and that's without talking about the BRIC countries whose middle class is starting to grow extremely rapidly and whose health care right now is a very tiny piece of their GDP. So the world is going to have even bigger numbers there in the long run. This is the positive slide. This is just several examples in the right-hand side of technology which has changed in major ways, changed the outcomes for people who have various kinds of diseases. This isn't just improvement in delivery of care. This is technology changes your outcome. I mean, one of the, I guess, favorite ones from my perspective is HIV, because it's such a pure molecular biology play. That virus still isn't 100% understood, but it's understood a lot better than it was. And because it's so well understood, a 3-drug cocktail, if you apply it religiously, can keep that virus at bay if you've been infected for almost everybody for years and years and years. So it's now a disease you can live with as opposed to a disease you would die with. And that's a really big change in healthcare. And if you look at total increases in longevity, these aren't my... I guess I should be more careful about... These are not my numbers. I can't actually guarantee that they're right, but this is basically saying that increase in longevity and technology are highly related to one another, and I do believe that's correct. VC-backed companies have not only created drugs that have been bought by other companies and technologies bought by other companies that are then put on the market, and we'll get into that in a minute, but they've actually created very large corporations, and these are in no particular order. Companies that are in the medical device area, Boston Scientific, very large biotech companies, some specialty pharma companies. A lot of jobs have been created, and a lot of technology and a lot of revenue comes out of these. Everybody asks the question, so what about healthcare reform, and how does that change our business, so the business of investing in small biotech, device, and service companies? Again, just going to the lower right-hand corner, just overall, there are 30 million new lives that are being insured by all of this. And yes, there are taxes, and yes, some of those taxes may not be all that fair. An excise tax, I don't think, on a company that loses money is particularly fair if you're trying to encourage technology innovation. But you can live with most of that if your revenue base goes up by that much. So the bottom line for device companies and the bottom line for pharma companies is, in the short term anyway, or the medium term, this is a good thing for them economically. More people will be getting more health care. In the service side of the world, which this seminar really isn't that much about, there are lots of changes, and this is the business. If you're delivering services in any place besides the United States, you don't invest in companies that do it because it's the government, for the most part, that's doing the providing of those services. This is the one place in the world where you can invest in companies that provide services of one sort or another, and it's always a guess as to how since the government regulates those services, how those regulations will change your investments. And it's a whole seminar in its own right, but some go up, some go down, nothing new there. And it's still an area where we believe, anyway, you can make significant money by investing. But on the technology side, I think it's just generally positive. So our favorite things that we can't control are on this slide. This is a highly regulated industry. That has its good side. The good side is regulation provides, in addition to patents, regulation provides barriers to entry. Barriers to entry are good things if you're an innovator because it keeps people from immediately following you. And so the FDA, EMEA in Europe, and the rest of the federal government actually, in some cases, help our companies or the companies that buy our products. On the other hand, the Europeans, if you rewind the clock and say, so what was it like 25 years ago? Say, nobody liked the FDA, but it was considered at that time the world's best regulatory body for medical care items. Scientifically reasonably savvy and reasonably predictable. Today, the FDA is about the same place it was, except it's a lot bigger and a lot more bureaucratic. Europe has gotten a lot better. They have a really good, in my opinion, regulatory authority. It's much more scientifically based than the FDA is. It's much more predictable. And of all things, Japan, which used to approve its drugs 10 years after we did, is now approving its drugs before we do. Again, in a predictable scientific way. So the world is changing, and we in the United States aren't. There are a number of specific issues here, some of which I'm going to talk about, where government regulation changes things. I'm not whining about the FDA because it's been something we've had to deal with all along, and it's probably not a lot worse than it was, but the rest of the world's gotten a little bit better. So we certainly could do better in this country. I'll come back to that. So where does the venture community fit into this? Well, we, other than trying to make money for the people that invest money with us, enjoy the fact that we create companies and medicines and devices and novel ways of providing service that weren't there before we started. In other words, innovation. So I don't know, I guess this is the most depressing slide that I have. What this says, and this is the I wonder where our business is going slide. I recover quickly with the next one, but this is all venture capital, not just healthcare venture capital. And it says that in the year 2000, an awful lot of money was raised in venture capital. And after that, it's tapered off a lot. Okay, so is the pool of money, the question that none of us know the answer to, is the pool of money that we now have access to, which is much smaller now than it was, large enough to support the entrepreneurial kinds of investments that we all want to make? I do not know the answer to that. It certainly was too big an industry, in my opinion, too big an industry in the year 2000. There was too much money chasing too few innovations. I'm afraid maybe we're at the position where there's too little money chasing too many good innovations, but we shall have to see about that. The reason for that is that the funds that were raised for the most, I shouldn't say for the most part, some of the funds that were raised with that large amount of money did not return capital to the people that invested them. So the people that invested them don't want to give their money, their pension money, back to people who didn't give their money back. So it's kind of obvious why that happened, but it is an oscillation that at least we all are having to live with, and not necessarily a good one. So this has led into healthcare. Healthcare business is a little bit, if you look at the capital going out the door, there's a lot of that's the orange line. There's still a lot of capital going out the door. That's a good thing. There's much less in the tech side than there was, certainly in the year 2000. And just as a footnote, Europe in healthcare looks like the US in tech. So it's a very anemic place right now. There used to be maybe 10 times as much money going out the door to fund innovation in healthcare in Europe than there is today. And yet the science in Europe is just as good as it is here. So it's really kind of an interesting marketplace over there. And since we have a European center, even though I would say the level of entrepreneurial management is less in Europe, the opportunities to invest are quite good. So again, all of that capital that was raised from 2000 till today, much of it is still sitting in people's accounts. So there's a lot of unused capital, and that has led to the fact that there are still a lot of deals being funded. There's a lot of capital going out the door, but if more capital isn't raised in the next 3 or 4 years, that's going to go down. So what about the entrepreneur side of the world? This is value created by the money we raise. Orange, first round. Well, when you're at a pre-money in healthcare, it's never been huge for most companies, of single-digit $1 million. The difference between, if you're going to raise during the life of a company somewhere between $20 and $100 million, whether you start at 2 or whether you start at 5 doesn't matter a whole lot. And the second rounds look pretty good as far as valuation. They've come down some. But it's a great time to invest, if you can find the right company, in later stage companies, because as you can see here, the later stage valuations have plummeted. And so I put that up. Our finance guy put the slide together. I put the do we get paid for starting companies up there. We don't show that to our LPs, okay? So there are ways to solve this problem. You raise enough money that you can do all of these rounds inside your syndicate, and then you don't have the problem of outside valuations. But in the old days, you didn't have to do that because the valuations went up because you put money in. So we have to change. One of the questions I got earlier in the seminar was, why aren't you so depressed about Obamacare? Why aren't you depressed about this and the other thing? We fund entrepreneurs, and if we venture capitalists, we can't change. It's shame on us for not being entrepreneurial ourselves. Change is not all bad. No money is bad, okay? There's not much you can do about that. But if the world of investment changes, then we have to change how we do that investment. And there is nothing wrong with that, in my opinion. It used to be that one could take so when I started being an entrepreneur, you could take a company public when you thought you had a drug invented. And then 10 years later, you could take a company public when you had phase 2 data that showed that the drug probably worked. Today, in a good market, which we're not in, you could take a company public when the drug is approved, with some exceptions. Why? Same reason that the people are not pumping money into venture capital. Public investors lost tons of money between 1980 and today because they couldn't tell the difference between a good company and a bad company. And if you invest in a market basket of all biotech companies, this has been true since the beginning, well, sorry, not quite the beginning, since 10 years after the beginning of the biotech industry. If you invested in a market basket, you lost money every time. If you invested in the good companies, you could make money in just about any time. But market baskets are what the public markets tend to do. Let's invest in kinase companies. Let's invest in molecular diagnostics companies. Let's invest in whatever. And you pick the 5, 6, 10 companies in the category. You invest in them if you're T. Rowe Price, and you lose money because only 2 of those companies were good and the other 8 went bankrupt. So that's not good. And our job as VCs is to invest in the 2 that work, obviously. And at least from a expertise perspective, we believe we're better at that than the public markets. But that does mean that our exits aren't going to be from taking our biotech companies or our device companies public almost all of the time. It's a double positive. It's supposed to be a negative. So most of the time, we will not be able to take these companies public. But the good news is we can sell them, because the dynamic that I'm going to get into now is that the folks that market devices and the folks that market drugs buy companies and buy assets of companies, and they're willing to pay them. Why? Because, again, as I will show you in later slides, they depend now on venture-backed companies for innovation, absolutely depend on it, and their CEOs say so. Those extremely expensive trials that one has to do to get registration and get past the EMEA and the FDA, they're really good at paying for those because they got a lot of money, but they are not so good at innovation. The deals have changed. There's a new gimmick out there called risk sharing. The large companies don't like taking on regulatory risk any more than anybody else does, so they don't pay us large amounts of money until that regulatory risk is removed. So they pay us a small amount of money, but the total deal size is often larger than it would have been if we hadn't shared that risk. So if we're successful with a drug, we can actually make more money than we used to. It just takes longer. So if you look at, this is about structured deals. So this is, instead of paying Glycify $400 million for its technology, which Merck did, these days, well, I don't know about Glycify, it's a platform, but a similar deal today might look like $50 million down, $100 million after you do a few things in some number of years, and then $300 million. Now it's 500 total instead of 400 total, and in 5 years. And so the number of structured deals like that have gone up. That's not good in the short term for us investor types, but it's probably not so bad in the long term. So what about the people that buy these things? This is the large pharma companies on the left-hand side of the slide. New drug approvals have, well, there's probably an uphill trend there. If you look from 1963 to 2007, a particularly good year after the FDA Reform Act was passed, but then right back down to the norm there. These are new chemical entities. There are all kinds of other drugs that are approved too, but the number is not large, right? We are talking 20, 30, 40 drugs. And that means if you actually get to one of those, you really have something valuable. So if you can last long enough as a biotech company to get there, you've got something that's worth a lot of money. If you look at the shaded part of this, the amount of money being spent by pharma to prosecute their clinical trials and their research is going up. Well, it used to be exponential. It's probably linear now. But it's very fast in that same time period. So much more money is being spent. A lot of that's because of regulatory constraints, but a lot of that is, in my personal opinion, what I call the girder problem. If you're in a small company, it's like being in a hut in the desert. You can put walls up, you put a thatched roof up, the place stands, you don't need any 2x4s, you don't need anything. You build a 2-story house, you need a little engineering, you need, corner joists, you need corner posts, you need joists, you need 2x4s to hold the wall up. You build a skyscraper, you need steel, you need concrete, and the bigger the skyscraper is, the more steel and the concrete are necessary to keep it in place. Innovative companies that are involved in innovation and research are often the same way. And I haven't seen a good solution to this, certainly not in our industry. You end up with the girders holding up these huge pharma companies that have gone through many, many mergers. So they don't duplicate their own work. They want to make sure that they're efficient. They don't have 2 sites working on the same thing. There's no internal competition. They have 7 committees before they can make a decision. Those are the kind of girders I'm talking about in our industry. I don't think you can innovate properly under those circumstances. And I think a lot of if you ask their CEOs, the Pfizer CEO recently gave a talk to the analysts and basically said, we give up. We're going to insource almost all of our R&D from a discovery point of view. We can't do it anymore. We're just too big. So innovation, assuming one wants to have it, there is a place for us in this business. There is a place in the food chain. And if you look on the right-hand side, the number of biopharma-originated drugs that are approved, blue, has gotten bigger over time. In 1995, it was 1/4 of them. Now it's 3/4 of them. So that innovative, now they're not marketed by the biotech companies for the most part that innovated them, but they are discovered by them. And so people need the stuff that our companies make. Can the pharma companies afford buying the assets? Answer, yes. So this is a Roche slide, actually. It's a couple of years out of date, but it takes into account the fact that a lot of drugs are going to come off patent. That's why these curves, if you add them up, start coming down. But if you look at the actual free cash flow after dividends, after patent expirations are taken into account, and taking into account drugs that people think will be approved. So this is an extrapolation. In 3 years, they can buy the entire biotech industry, all of it. They don't have a cash problem. They may have a problem, but it's not a cash problem. So the right-hand side will lead to the next slide, and that is that if you look at, so the way, with the exception of biotech drugs, which are protected by process as well as patent, and we'll get into that in the second part of the seminar. If you look at small molecule drugs, they're patented for 17 years, used to be, now 20 years from filing. And when that patent comes off, the price, basically the market goes from whatever it is, $5 billion to 0, essentially, for that innovator in 1 year. And the generic market takes over. Different companies, totally different business model. And this shows you how many $1 billion of sales are coming off patent, in this case between 2011 and 2013. $113 billion per annum in sales will disappear from the big pharma companies and reappear as a smaller number in the generic companies. And it's been bad in the past, but it's really going to get bad in the next several years. And so a lot of these companies are, so if you want to know which company to worry about most, you shouldn't worry too much about GSK because they fell off the cliff a few years ago. That's the only reason they look like this. But Lilly, and by the way, Lilly's doing some fantastic stuff to make this not happen, to make this not hurt them. But if they just sat there and did nothing, didn't have any new drugs, they'd be losing an enormous amount of their, most of their revenue, one would argue, before very long, before many years are up. So if you're sitting in that company, you're looking for new things and you're looking for innovation because you have to replace that which is going off patent. It's not quite that simple, by the way, and it's not quite that bad because Lilly, for instance, is a biotechnology company, and a lot of their drugs are already, insulin's already off patent, and it's $1 billion drug, and it's not going anywhere, right? So, again, I'll get to that in a minute. This is consolidation, mergers, little companies being bought by good ones. That's a good thing. Big companies being bought by bigger ones. That's not a good thing. Fewer customers. It's a problem for us. And not only that, they go into paralysis for at least a year and a half after they. So Merck swallowed shearing plow. Merck hasn't done a big acquisition since it swallowed shearing plow. They're still digesting it. And when they're finished digesting it, they'll come up for air. But it's, and there have been a recent spate of mega mergers which have reduced the number of customers and also led to this sort of paralysis. So pharma, however, forget the ones that swallowed other things. Pharma is doing more deals. That's all this says. That's what this slide says. These are the numbers that support it. And I'm not going to go through this little graph for anything except to show you that when a company is sold in its development, this is a drug company, not a platform company. And in fact, I'm only going to talk about one drug company in the second part of this presentation and many platform companies. And this is irrelevant for a platform company. But a drug company spends, from the time somebody has a brilliant idea, 8, 9, 4 more, 12 years probably till you get to the market. And from the time that you say, I have discovered a drug, that would be about here, it's about 10 years. Okay? So between 8 and 10. That's a long time. We tend to invest right about here. Right about here, phase 0. And when you show the drug works, when you show it affects the disease of interest, what you do not want to do in a biotech company is to go out here in phase 3, where you're spending for a small disease $40 million to get your drug on the market, and for a cardiovascular disease $200 million to get your drug on the market. If you're not public, you don't have $200 million. Even the biggest funds don't have that kind of money. They have the money for the smaller diseases, and hopefully they can invest in them and bring them to the market if they have to. I'm involved in one such company that has a cystic fibrosis drug. But if you're talking about a major cardiovascular disease or diabetes, you can't afford it. Only those guys in that graph I showed with all the Jacob's coat of many colors slide, those guys can afford it, so you have to sell it. And what this says is there are times where value changes stochastically, and it's different for every drug. These are drugs and devices, drugs left, devices right, that our firm has invested in over time. It's nice to know that what you do actually does make it to the market in addition to making money. And I would say if you look at the pipeline of things that are in phase 2 and phase 3, it's a lot more interesting even than this. So now I'm going to talk about, race through actually, 5 companies, 2 of which come out of Dartmouth, and 1 of which comes out of Stanford, 1 of which comes out of Genentech almost, I guess you could say, and 1 of which comes out of Harvard. And I'm not going to do any of these companies justice. I'm simply going to say a few words about each one that says why they're cool. Okay? This is why are these companies cool, and what did they do that had an either economic or a technological interest, and what sorts of technologies needed to be invented in order to make them be successful. So as you know, Glycophy's intellectual roots were right in this building. Charles Hutchinson, who is here today, and Tilman Gerngross, who is also here today, are the founders of this company. The business plan got written on some napkins, which have been framed and given to the founders. What was on the napkin actually happened. That's the miraculous part of this. There are many business plans on napkins that lead to great companies, but most of the time the napkins have nothing to do with what the company ends up doing. It did in this case. Just to remind you, I know you've probably seen a lot of these before, but some of you may be new students and some of you may be new guests. This is a picture of a protein. Protein is made up of many, many atoms. Each one of these, the vertices of this model is an atom. This is the protein backbone of a glycoprotein. The protein itself is made on a ribosome, and if it's a glycoprotein and it's made in a eukaryotic cell, that's a cell with a nucleus, often that protein is decorated with sugars. And the breakthrough that Glycophy embodied was to understand how to engineer those sugars in a way that is not possible yet anyway in higher eukaryotic cells. So most of the therapeutic proteins that are on the market are glycoproteins, so proteins decorated with these sugars. And the sugars have a complex structure to them. They're complex when they're put on, and they're complex if it sits in a fermenter a long time and they get degraded. So all the drugs, every single glycoprotein on the market, every single antibody on the market is heterogeneous right now. It's not homogeneous. It's a mixture. And what Glycophy allowed you to do was engineer homogeneous glycoforms. As you will see in a later slide, this is a simple one. Okay, so these are cartoons of those sugars, different kinds of sugars that can be decorated on a single site of a protein. And if you take a mass spec and look at those sugars, you see in a typical mammalian cell culture derived glycoprotein a mixture. And it turns out that those mixtures have different biological responses. And if you're going to make a biosimilar drug, and we'll get to that in a minute, those mixtures have to be the same or you will get different biology in a human being. And what Glycophy showed was that you could make individual, separate components that are essentially homogeneous using the yeast engineered technology that came out of this place. Pretty amazing. And pretty amazing set of publications that came out of that. And this is the final publication that showed that you could actually make a very complex protein, erythropoietin, in this yeast system with human sugars on it. Again, a platform technology, a very successful exit, something which unfortunately I think the commercialization has been much slower than the invention. So once Merck had it, it hasn't gone as fast as any of us would be happy with, but we got it as investors, and the team that Tilman and Hutch hired got it very quickly to the point where it could have been commercialized. So this is another company. Sutro comes out of Stanford and Genentech. Jim Swartz is the founder. This is a company that makes proteins outside cells. It makes proteins in stainless steel tanks at scale. Sounds kind of ridiculous. People have been able to make proteins outside of cells for a long time, but they have to feed them things like ATP, which are incredibly expensive. This actually runs the Krebs cycle, for those of you that know what that is, in the tank. You feed it glucose, you bubble oxygen through it, it makes energy, makes the ATP and the GTP itself in that tank, and ribosome. So all you got to do is take this extract, which you can preserve, put in tank cars, store forever, put it in the tank, inject the DNA for the protein you want to make, and somewhere between 6 and 12 hours later, you have about 1 gram per liter of protein. And that, I mean, frankly, when the founder came to me and said, I can do that, I said, you are smoking something, because it doesn't sound possible. Well, it actually is possible. So this is just a cartoon of what I said. So the energy, in this case, comes from sugar and oxygen, the cheapest energy you could come up with, actually, well, it's certainly cheap enough for making biochemicals. The input is DNA. It can be synthetic DNA. It doesn't have to even be on a plasmid. And you can make, well, in this case, it's showing you can make a Fab or a whole antibody. You can easily make multi-domain eukaryotic proteins. And if you look at the bottom of the slide, the process is linearly scalable over 10 to the 7th fold. So once you figured out how to make a given protein in a drop, you can make it at 1,000 liters, and you don't have to change a darn thing. Well, try that with a cell. It's not possible. So it means that you can do process engineering in a microtiter plate. It does not mean you have to do it in a fermenter, and that changes a lot of things, actually. It makes disulfide. This turns out this is GM-CSF. It's a globular cytokine protein, modest size, molecular weight. And this just shows, regardless of scale, 250 microliters, 100 liters, 1,000 liters, you basically get the same synthesis rate and quality of protein, no matter what scale it is. This is going to be in a paper soon, and I'm not going to go through the details of it, but one of the questions is, well, so you're making this stuff in a big fermenter, there must be editing things in cells. Cells make proteins they make great proteins. If it says put a lysine in, it puts a lysine in, right? There must be an editing function that's going to be missing in your giant fermenter when you do this at scale. Well, it's not, actually. It's about 10-fold better than E. coli does, because E. coli is doing a bunch of other things, and this is making one protein. It's not alive anymore. So that ribosome's only doing one thing for its living. It's making that same protein again and again and again. And when it does it, it makes the same protein with very great fidelity. And this kind of data, by the way, is going to be necessary if you're going to put anything made by this technology into human beings, because the FDA is going to say, what? You're not making it in a cell? Tell us how good this stuff is. This is a bunch of different runs at a bunch of different scales. No, actually, it's the same scale. Sorry, this is a 10-liter scale. And the point of this is, why does it stop at 10 hours? Why, what is the rate-limiting step? Is it running out of, what's it running out of, for that matter? And the group at Sutro has done a tremendous job over the last few years doing engineering to figure out what's rate-limiting, what needs to be added back, and during that process, they've managed to approximately triple the yields of what they get out of it just by essentially mass spectral analysis. And the last thing they can do is they can put in any old amino acid you want in a protein, not just the 20 that nature gives you. And that's doable in a way which I'm not going to have time to explain, but just pretend it's magic for now. But you can also do that at full scale, and probably at only twice the cost per gram of regular proteins. And the example I'm going to show you here is putting something that allows you to do click chemistry into a protein at 3 different places. And the reason you have 3 different molecular weights is because it's substituting for a different amino acid at each one of the 3 places. And then I'll show you in the next slide that you can use this to put another protein as a conjugate on the first protein. So now you can paint with a chemistry palette that's whatever you want to paint with, right? You can make a protein that's essentially homogeneous, and you can put in 1, 2, or 3 different kinds of amino acids any place you want to. And that is not a native amino acid, by the way, at the same sorts of fidelity you're talking about before. So this is hooking on green fluorescent protein to a globular protein This was done 3 different times, so there are 3 different experiments, but I'm not going to show you that. Very cool stuff. And next cool stuff, we're back to Dartmouth and MIT. This is a monoclonal antibody discovery program, ADIMAB company. ADIMAB, again, Tillman and Dane Wittrup in this case are the co-founders. Antibodies are the largest class of drugs that are being approved because of the fact that they survive patent expiration. Pharmaceutical companies love them. The technology that ADIMAB has created allows you to make a human immune system in a yeast and to make a separate library of up to 10 to the 10th different antibodies and display one antibody on each yeast cell. That's one antibody on each yeast cell. And if that antibody on the center cell here happens to be the right antibody to capture the antigen you're after, and that antigen in this case, again, is fluorescent, you end up labeling the yeast cell with the fluorescent protein. There's a very cool technology that was developed for other purposes called fluorescent cell sorting. This is just a cartoon of how that works. It separates the fluorescent cells from the non-fluorescent cells. You put, so the yeasts are on the left, the fluorescent proteins are the little green dots there, and they bind to the yeast that's interesting. You put through the fluorescent cell sorter. You collect individually in individual cells the various yeast cells which bind. So now you have a different yeast cell in each well. Each yeast cell binds that antigen that you're interested in. So you've now gone from 10 to the 10th down to a well of 96 of them. You change the conditions of growing that yeast. Instead of being on the surface, now you're making that antibody in solution. You purify the antibody, and in 8 weeks from the time you started your little experiment here, to the time you deliver 2 or 3 96 well plates worth of antibodies is 8 weeks. To do this by injecting mice and other ways, actually other in vitro ways, the competitive technologies are more like 8 months. So it's an amazing, amazing technology. I'm going to zip through this next slide. These are the customers that ADIMAB has to date. And one thing, and by the way, a great collaboration with Google on the information technology side. Spin-offs and small companies that ADIMAB can collaborate with, some of which have been done and some of which have yet to be done, to allow ADIMAB to use that technology and keep more of the goodies than they would by licensing it to large companies. Again, a great technology, much better than anything that's out there. Last 2 companies very quickly. Biosimilars. So this is showing you how hard it is to make glycoproteins that are the same. I'm not allowed to tell you what the glycoprotein here is, but if you remember back to that first picture I showed you with Glycofy, where it had like 6 peaks and it said, this is what's made in a cell. Wait till you see the next slide. So to make a biosimilar protein, you have to basically show that within the manufacturing processes of the protein it's made by the innovator, you make proteins that are more tightly quality controlled than they do. So this is what this particular set of glycoforms looks like. There are over 100 major glycoforms for this protein, and you have to show, if you're going to make a biosimilar, that all 100 of them that count are there in approximately the same ratio. So this is an example of several hundred experiments of this sort that you've got to do in order to prove this. So this looks at a single glycoform at a single site here, a single structure, I should say, and asks the question, what is at the end of the tips of this sugar chain? And this shows, I can't remember what color is what, but Some of these are innovator products that are sold today on the market, different lots of them. They've analyzed 50 lots of them, and there are 10 lots of this biosimilar, and you will not be able to tell the difference between them. So I'm just going to zip through these. This is, there are literally 100 of these together. So they had to come up with great technology to do this, and data to show that you actually have a biosimilar. They've taken this data to the FDA. The FDA says, yes, this sure looks biosimilar to us. So they have since sold this product to somebody, and I can't even tell you who they sold it to because the company wants to keep it a secret, and it's now being developed as a biosimilar to be sold in what is about a $500 million market. This is an analytical tour de force. It's done by a team of people that have developed many drugs in their lives, but it kind of, if you want to compare this to Glycify, it tells you how difficult this kind of production technology is. Again, just another way of measuring things. And the last one is this is the diabetes company. A very simple idea, and we think a very good one. So this is a company we invested in. We put $1 million up because we said this is ridiculous. This is just way too easy. This can't possibly work. We want to see it repeated, and if it repeats, then we'll give you some real money to develop the drug. Well, it has repeated, and I will show you the simple idea. It starts out with data from a guy named Steve Schulson, who is in Harvard Medical School, and he's shown that salicylate, that doesn't mean aspirin, by the way, but salicylate, given in very high doses, grams, spoonfuls per day, 3-4 times a day, actually lowers inflammation, and I'll get you data on why that's interesting, in patients that have type 2 diabetes, and that inflammation lowering changes their blood sugar and therefore their diabetes side effects. This is not a drug, it's a proof of principle. You don't take 4 grams of spoonfuls of salicylate, which by the way give you terrible ringing of the ears at this kind of dosing. But it does show you that inflammation, that just changing the inflammatory state of your body can change the outcomes of diabetes. So salicylate's the oldest drug I know of. It started off with the Sumerians in 6000 BC. There were writings, the Egyptians used it to draw the heat out of inflamed wounds in 1500 BC. Hippocrates talked about it at 400 BC, and that's an example of that. Right down through Galen, who is the last person on this, it's been written up in the literature. It's willow bark, okay? So it's pretty simple stuff. It's a very, 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 very old drug. Inflammation is the basis for a lot of disease. Maybe you guys don't know this, but it's important in things that look like inflammation. It's involved in Alzheimer's. It's involved in bone and muscular disease. It's involved in diabetes, and it's involved in cardiovascular disease. And again, not to go through this in great detail, but if you can change, the hypothesis of this company is if you can change without giving 4 grams of salicylate to a human being, their state of inflammation, you can actually change the outcome of diabetes. So what they came up with is a simple conjugation technology that takes fish oil. You've all read about fish oil. You probably have. Some of you probably take it as a supplement. And they conjugate it very simply with a linker that only gets taken off at fat cells where this inflammation occurs. So they add fish oil to the salicylate. That's the technology of the company. It's not just salicylate, but fish oil plus X is the technology of the company, and this is the first product. And that their hypothesis is that since fish oil is anti-inflammatory, salicylate's anti-inflammatory, that you can actually deliver this stuff where it belongs at much, much lower doses. And salicylate is a pro-inflammatory pathway reducer. DHA or fish oil is an anti-inflammatory. pro-inflammatory, yes, reducer, and DHA is an anti-inflammatory pathway compound that increases that. Together, they're synergistic. And last data slide here, actually. If you look on the left, the compound that's the conjugate works at about 20 micromolar. If you look at salicylate, it works at about, let's see, 1 molar. So a huge difference in efficacy and synergy between the two compounds. This is just animal data that shows you can normalize glucose, you can normalize insulin, and you can normalize hemoglobin at A20C. Basically asking the question if you have diabetes or not. Glycated hemoglobin is one of the side effects of it, and easy for you to measure in clinic. And this is in a mouse that is diabetic because it eats too much. So it's diabetic for the same reasons that humans get diabetic. So this is a company, again, great promise. I know what the odds are that it's going to cure diabetes, but it's one of the few things out there where it actually changed the course of the disease because of the underlying reason that you got the disease in the beginning. Again, a very exciting investment. So those are the companies, venture capital thing at the front end, and thank you very much.
We have time for a few questions.
You mentioned that the European regulatory environment is now much more efficient now. Are you taking American developed drugs and trying to get them approved in Europe? And also, why, if the approval process in Europe is much more efficient than the FDA process here, why is there a venture money for medical for drugs so why is it so small in comparison to the U.S.?
Okay, so there isn't a perfect place to sell and develop drugs. I would argue that Europe is a great place to develop drugs. Europe is a great place to develop drugs, but it's not necessarily a great place to sell drugs. If you actually look at the cash flow of research innovation, the United States, the sales of drugs in the United States pay for the development of drugs in Europe because we charge more for drugs in this country. And so, yes, companies do. I mean, it's not that you don't want to sell drugs in Europe, but the pricing is sometimes as low as 0.1 times what you would sell them for here. And if that was all you ever got, you couldn't afford to develop the drug in the first place. So it's sort of a yin and the yang problem. France and Germany have pretty fair drug pricing, but England, as an example, doesn't.
More questions?
Yeah. Do I think that will change? No, what will happen is that our drug pricing will slowly come down because the United States citizens are probably not so happy about financing the health care of the rest of the world. And sales in BRIC countries, in China and Russia and Brazil and so on, are going to, and India, are going to become an increasing part of the pharmaceutical market. The United States will become less important in the whole business. It's not that we won't get the innovations. And what happens in 10 years, I can't tell you. But those are the sort of trends right now. And Europe is not about to start paying more for drugs, no. In my opinion.